Hello students, in last lecture we have seen the construction of unijunction transistor. Now in this lecture we will see the working equivalent circuit and IV characteristic of unijunction transistor. So now moving towards the working or operation of the unijunction transistor. So the unijunction transistor can work in two ways. That is, first one, when no emitter voltage is applied, that is emitter terminal is open, and the second case in which there is some voltage is applied to the emitter terminal. So when the emitter terminal is open, that is no emitter voltage is applied or voltage is not applied to the emitter terminal. This is the N-type strip and this is the region which gives or which visualized as a voltage divider circuit. That is, for this B1 terminal it will give the resistance which is RB1, and for this B2 terminal the resistance which is offered which is RB2. Okay, and when there is no voltage is applied, we will consider the equivalent circuit for this situation. So this is RB2, this is RB1, and as the unijunction transistor has a single PN junction, so it is equivalent to a diode. And this is the emitter terminal which is open, and between the two bases, that is base B1 and base B2, the battery is attached. That is, positive terminal is connected to B2, that is base B2, and negative terminal of the battery is connected to base B1, and the voltage drop across this is denoted as VBB. And when the emitter terminal is open, then as there is a positive potential at this RB2, so if we take into consideration this point A, then it will become positive, and this at the terminal B2 it will become negative. So the voltage drop across this RB1 is denoted as V1. Okay, so if one has to know how much voltage drop is observed across this RB1, then it may be given as it is equal to the resistance, original resistance is RB1 divided by the total resistance, that is RB1 plus RB2 into this potential, that is VBB, and this ratio, that is RB1 by RB1 plus RB2, is nothing but it is eta VBB. So the potential drop across this RB1 is given by given by the factor eta VBB. So this potential across this is V1, which is given as eta VBB. Eta VBB. So this is the first case when there is no voltage is applied to the emitter terminal. and as no voltage is applied to the emitter terminal, this point becomes positive, due to which this diode is in reverse bias, due to which very less reverse bias current is flowing, and which can be neglected. So this is the first case. Then we will see the second case, when the voltage is applied to the emitter terminal. So when voltage is applied to the emitter terminal, the voltage drop across this diode is given by VD. Okay, this is the voltage drop across the diode, and VE is the potential across this emitter, potential across this battery, which is provided by the battery, which is attached to the emitter terminal. Then in this case, as positive potential is given to the emitter terminal, and this is the P region, the small inner curved region is P region. So number of holes from P region may be ejected outside to this N-type strip, and as the positive terminal from this VBB, as the positive terminal of VBB is connected to this base B2, due to which these holes which are injected from this P region will move towards this base B1. Okay, and due to which current will flow in this direction from P region to base B1. And in this case, as this positive terminal of this battery is connected to the emitter terminal, this PN junction is in forward biased. So there will be two cases for these two situations, when VE is less than V1, that is V1 is the potential across this RB1, and when this happens, this PN junction remains in reverse bias, that is when there is no voltage is applied in this case also, or when this VE is less than V1, then this PN junction remains in reverse biased. PN junction remains in reverse bias. But when the point reaches, or this voltage VE is equivalent to the diode voltage for the silicon, it is 0.7 electron volt. So when this V is become equivalent to that much of voltage, the current start flowing, and this PN junction becomes in forward bias. So eventually, after V, when it becomes greater than V1, the PN junction becomes forward biased, because when this V is greater than this voltage drop across this RB1, that is voltage drop which is developed at this region, then current start flowing, because holes from P region will be injected to the N-type strip, and as this B1 terminal is connected to negative terminal of this VBB, these holes may be attracted towards this B1 terminal and current starts flowing, due to which this PN junction becomes forward biased. So we will move towards the equivalent circuit of UJT. So this is the equivalent circuit of UJT, as unijunction transistor is a single PN junction, so it is equivalent to the diode, and as the P region is near to the B2, so it will give the or it is equivalent to the voltage divider circuit. So it will have the two resistances, that is RB1 and RB2. So with change in emitter voltage, there will be a change in RB1. So this RB1 is variable resistor, and there is no any change with the RB2, because with change in V there is no any change, that is this positive terminal of VBB is connected to the base B2, due to this positive potential at the B2, the holes may not be attracted towards B2. So this RB2, that is this resistance provided by this region, will remain constant, and as voltage increasing, due to increasing voltage, there will be number of holes which are injecting from this P region towards the B1 terminal will increase, that is there will be increase in current, and due to increase in current there will be decrease in resistance, that is decrease in RB1. So this is the variable resistor. Then previously we have seen the voltage across RB1, which is equal to eta VBB. So it is the voltage between this point and this negative terminal of VBB, and the potential across base B2 and base B1 is given as VBB. So the resistance RBB in this case, that is resistance across the base B1 and B2, which is given by RBB, which is equal to RB1 plus RB2, and the value of this RBB lies between 4 kilo ohm to 10 kilo ohm. 4 kilo ohm to 10 kilo ohm. And previously we have seen the potential drop across this RB1, which is given by V1 is equal to RB1 upon RB1 plus RB2 into VBB. Or this V1 is equal to eta VBB. So by taking this equation, we may rearrange this equation as V1 by VBB is equal to RB1 upon RB1 plus RB2. And this V1 upon VBB, this ratio is called intrinsic standoff ratio. This V1 upon VBB is called intrinsic standoff ratio. Standoff ratio and which is denoted by letter eta, which is denoted by letter eta. So eta may be written as eta is equal to V1 by VBB, or it can be again written as, from this equation, it is equal to RB1 upon RB1 plus RB2. So this is all about the intrinsic standoff ratio. Then we will consider the next point, that is when the input voltage exceeds the eta VBB. Input voltage, that is VE. When this is the input voltage which is given by VE, when this VE is greater than eta VBB by VD, that is VD is the diode voltage, the forward voltage drop across the silicon diode is given by VP is equal to eta VBB plus VD, and this where this VP is called peak point voltage and VD is called forward voltage drop across silicon diode. VP is peak point voltage, peak point voltage and VD is called forward voltage drop across silicon diode. So this is all about the equivalent circuit of unijunction transistor. Then we will see the IV characteristic of unijunction transistor. So initially, when there is no emitter voltage is applied or very small emitter voltage is applied, the PN junction at the starting point, when no emitter voltage is applied, the PN junction is in reverse bias, and when slowly we increase the V, we found that the voltage is increasing with increasing current, and this current is the reverse saturation current, which is given by IE0. This is the reverse saturation current or reverse current. Then we observe a point at which up to which the voltage is increasing with increasing current, and after that particular point the voltage is decreasing with increasing current. So this point after which there we observe the decreasing voltage with increasing current, this point is called peak point. So corresponding voltage is peak point voltage, which is given by Vp, and corresponding current is given by peak point current, which is Ip. Then in this region, as there is decrease in voltage with increasing current, there we observe a point at which there is a minimum point, or after that point there is increasing voltage again. So this minima is called the valley point, and the corresponding voltage is VV, that is valley point voltage, and corresponding current for this point is valley point current. So after this valley point, the current increases suddenly, and this region is called saturation region, and the region between peak point and valley point is called negative resistance region. So this is all about the IV characteristic of unijunction transistor. So with this I will stop here. Thank you.